Okay, welcome to the next lecture of ECE 1756. Today we're going to be talking about, we're done with compute models. We're going to be talking about how FPGAs compare in terms of efficiency to some other devices, CPUs, GPUs, and ASICs, to try to get a lay of the land. Okay, so before we go into that, let's talk a little bit about administration. Assignment 1 is due a week from tomorrow, so hopefully that's going well. Any thoughts on it so far? How is it going? See if any brave soul wants to venture weigh in and say it's going well or it's going poorly. So hopefully most of you have started it. It's always a high stress technique to leave it to the very end. So if you haven't started yet, start now. Not too late to do it without undue stress, but it'll get stressful if you leave it to the end. Reading for this week, so we're going to go over both these papers. The Yanacoris paper, which basically compares a processor style of programmability, a processor compute model versus direct hardware execution, and a paper that compares peak performance on a bunch of different kinds of devices. So we'll go over that a little bit later in the lecture. For next week, you've got multiple options for reading. So 2 papers that we'll discuss in class, and you'll get a lot more out of that if you read them in advance. Plus, as I said a couple times, you have to submit at least 10 summaries of papers or questionnaires on papers to have a hope of getting a full 10% on that part of your mark. So the first paper is a few years old, but I think it's a good exercise in very careful benchmarking. It's a work by Intel where they take a bunch of papers that were published with very large speedups on GPUs versus CPUs, and they basically look at those studies in detail and try to reproduce the results and see if it really is 100x speed up when you go from a GPU to a CPU. And if you can't wait to know the answer, then go read this paper this week. It has important lessons for all benchmarking, I think, including when people are trying to get a speed up on FPGAs versus CPUs. Second paper is about FPGAs in the data center. So FPGAs have traditionally been deployed mainly in deeply embedded applications. So special purpose boxes, wireless base stations, washing machines, automotive electronics, high-end core routers that are moving data across North America or elsewhere. So that's where they've usually gone. But recently being, in the last 4 years or so, or 5 years, they've also started to move into data centers where they basically accelerate whatever you need accelerated at any point in time, or at least that would be the ideal of how to use them in a data center, that they would provide a new kind of acceleration for a variety of applications rather than what they've done in the past, which, as I said, is be efficient for one kind of functions in a certain box. So this is an interesting paper from Microsoft about how did they do that. And Microsoft has gone pretty big in on FPGAs in the data center. So they're not the only data center provider that's put them in their data centers, but they've definitely made a bigger bet than anybody else. So this is an interesting paper on basically their second generation of trying to put FPGAs in the data center, which is the one that they really went big with, where they rolled it out through the whole data center. There's another paper that's optional, and you can write a summary on it as well if you'd like to get all these summaries done or have many chances to get full marks. It's the first version of that Microsoft data center FPGAs and data center project, which is called Catapult. So the reason it's optional is it does overlap some with this second paper, but not completely. This 2014 paper on Catapult really is a great paper, even though in some ways it's been superseded by the follow-on paper from Microsoft. So if you've got the time, it's a really interesting one to read too. It has a bunch of other detail that you won't get from the 2016 paper. As I said, we'll talk about the first 2 papers, and bits of the third paper I'll also pull into the lecture next week. All right, so that's the reading. So it looks like people are going fine with, I got a couple of comments at least. People think that assignment 1's going fine and isn't too hard, so that's great. Okay, so what we're going to talk about today is Yeah, FPGAs versus other devices. So I love FPGAs. They've been good to me in my career, but you need to know, what are they good at? What are they less good at? So let's look at how they compare to other things. And this is going to be from 10,000 feet, meaning I'm not going to, in one lecture, try to explain CPUs, GPUs, DSPs, FPGAs, etc. in great detail. So, jump in if you have thoughts where you go, hey, you glossed over that or you're wrong. That makes it actually a lot more interesting. But if you're hoping that I will make clear all architectural choices and all programmable devices in this one lecture, I am going to disappoint you, but I hopefully will give you an interesting overview. Okay, so let's talk about CPUs. So CPUs are, the default choice. If you can do it in a CPU, and we talked earlier in the course about sometimes you can't do it in a CPU because you actually can't connect to the right things. So if you need programmable I/O, a CPU can't do it. The other reason is maybe it doesn't give you enough performance. But if it does, it's probably your go-to choice. It's going to be the easiest, simplest programming model. You're going to get going fastest. Okay, so what's in a high-end CPU? Well, you've basically got this is a very high-level block diagram, and it's courtesy of Mike Houston of AMD. So you're going to bring in instructions. So CPU has no idea what to do unless you give it an instruction. So you're going to fetch and decode instructions. And those instructions are going to tell you what to do. It's going to control your ALU, which is your actual execution units, your shared data path that does something. And in order for that ALU to, get data and store temporary results, it needs an execution context. So what is the execution context? Basically the register file. It's the register file and main memory. So your execution context, you've got some of the data relatively close to in your register file, and the rest of the data is in main memory. So that is a CPU. And then you've got a bunch of things to try to make it faster. So CPUs really are trying to maximize single thread performance. They're originally built to take a single program and run it really fast. And typical programs have lots of if statements. So what do? They have out of order control logic, meaning there's a stream of instructions that they have to execute. And they can execute that stream faster if they look ahead in the instruction stream and see, well, what could I do? Maybe the next instruction I can't do right now because it's waiting for some data to be computed, but maybe there's some other instructions further ahead that I could work on. All high-end CPUs do that. They execute instructions out of order. It takes a lot of control logic, a lot of data tracking to hide this from the programmer. It appears that it executes all the instructions in order, but in reality, it's not. It takes a lot of hardware to make that happen correctly. Okay, there are a lot of if statements. So, and every if statement, it's going to take, this CPU is deeply pipelined to run quickly, so it's going to take a long time for us to figure out whether we take the branch or don't take the branch. So we take the if or the else. That's going to stall our pipeline and really slow our processor down. So we have a fancy branch predictor. Spent a lot of hardware trying to guess very quickly, early on, way up here in fetch and decode, what is going to happen in this branch. I don't actually know yet. I have to wait for various conditions to be computed, but I want to predict it so that I can keep speculatively executing what I think are the next instructions so I can keep my pipeline busy. And if I usually guess right, I get more performance. Well, I'm running one thread. So if I have to wait hundreds of clock cycles for data to come from memory, I stall all of my execution units, I stall my whole pipeline, and I waste time. So I don't want to do that. So I have a memory prefetcher. So I got a memory prefetcher is trying to guess what data am I going to need next from memory and go grab it, issue the request a long time in advance, ideally tens or hundreds of cycles in advance of when I actually need it, so that it's already been brought into my data cache by the time I need it. So I rely on all of these things to keep my processor running smoothly on this one thread that it was built for. And the data cache also helps, right? It takes hundreds of cycles to wait for data from main memory. So if I've got a big data cache, its latency is much lower. It's several cycles still, but I can tolerate that a lot better with things like out of order control logic and a fancy branch predictor. So if I can get all the stuff I need into the data cache, I can keep this processor running quickly. Okay, so they were built to maximize single thread performance. Now they've moved away from that some. That's still the primary goal in a high-end CPU. You don't want to compromise single thread performance, but basically to get more single thread performance is becoming extremely hard. Clock frequencies don't scale up very much anymore because this CPU is already very deeply pipelined. So it's just 300 picoseconds or so for pipe stage, and you just can't go much faster than that. And we can try to execute more instructions from this one thread at once, but the complexity of this out of order control logic, these branch predictors, these memory prefetchers, they're all growing rapidly as we try to do more instructions and keep the CPU busy. So there are diminishing returns trying to speed up a single thread. So companies like Intel want to sell you lots of CPU silicon. So what can they do with their silicon budget if they're not going to get much more single thread performance? Well, the first thing to do is they have multiple cores. Okay, so depending on what class of machine you're buying, if you're buying a laptop, you're probably going to get 4 cores nowadays. If you go buy a very high Xeon server and you will pay a lot of money for that CPU, then you might get 24 cores for a very high-end, kind of multi-core big machine. So that's one thing to do, is just take this high-end CPU and basically replicate that core multiple times, so that's one way you can work on multiple threads. You can be executing multiple programs, or within one program, if it's got multiple threads, these cores could be collaborating. The other thing that they do is they allow SIMD, so single instruction, multiple data. Instead of sending an instruction that just says, add 2 numbers together to the ALU. So maybe whoops, I shouldn't have done that. Let's see if I can go back here. Instead of saying add these 2 numbers together in my ALU, like a simple add operation, you could have a SIMD instruction that says add 4 pairs of numbers. So it's still one instruction, but it's really saying do a whole bunch of additions. And I'm going to show you that that's been gradually, the amount of SIMD has been gradually increasing in processors. Partly because how do you spend your silicon budget? You can't spend it efficiently on just doing more of the same, more of these out of order and branch predictors, etc. You do a little more of those each generation. So each generation, high-end CPUs get a little faster in single thread performance. But the transistor budgets are growing much faster than they can leverage. So they go for 2 other kinds of parallelism, multiple cores and data path parallelism with SIMD. So let me pause there. So any questions on that? Does that all make sense? I see Andrew has no questions, so he gave me the thumbs up. So thanks, Andrew. Okay, I'm going to take that. I see a yes. So I'm going to take the thumbs up and the yes as general agreement. This is like the easiest election to win. You vote, you may just carry the whole day by yourself. Okay, so let's look at a GPU. So how is it? A GPU is still a processor. So it still has an instruction stream. You fetch and decode the instruction, and that tells you what to do. So how is it different than a CPU, a traditional processor? Basically where it spends its transistor budget. It has simple control. So it doesn't worry about these fancy branch predictors. It doesn't do out of order execution. It's going to execute the instructions in the order that you give it to it. It's built for SIMD. So processors have SIMD, but it's kind of not their primary goal. It's not a negligible goal to be reasonable at SIMD, but they really want to be good at single-threaded performance on programs that are just processing one data item at a time as well, scalars. Graphics processors care a lot about SIMD. So they know they're working on graphics. Graphics is still the original market and still the largest market for graphics processors. And graphics has huge amounts of parallelism. You can mostly compute the value of 1 pixel without knowing the value of the pixels around it. So that allows you to exploit things like SIMD, where you say, instead of doing 1 pixel, let's do 8 pixels at once, or even more. So they use SIMD aggressively. They started with 8-way SIMD, and it's gradually increasing. And basically, it amortizes their instruction cost. So they still have this instruction, which they have to decode, and it controls all of their execution units. So they have all this shared hardware controlled by an instruction, which we already talked about. That's not the most efficient way to do things. But if you say I've got one instruction and that instruction is going to control a whole bunch of ALUs who are all going to do the same thing, okay, I've amortized my control a lot. I get a lot more efficient if I have enough parallelism. Okay, they also don't have, their memory structure is different. They don't have this big data cache. They don't have fancy prefetchers, etc. What they instead have is they have a whole bunch, instead of one big execution context, which is what we had, if I go back here on the CPU, we had one big execution context, register file, main memory, okay? The graphics processor basically divides its register file and its main memory across many execution contexts. So that's what this is showing here. And there might be some shared data between them, but mostly, you know, the GPU programmers trying to separate out data so that we can have many threads, each of which has their own execution context. So they're not looking at the data of other threads. Okay, so they're fundamentally built for multi-threading. Instead of trying to make one thread fast, where you're trying to find, you know, sequential instructions in an instruction stream and overlap them as much as you can, the GPU just says, give me a whole bunch of threads. I'll launch a read to main memory for one thread, and then I'll just immediately switch the next clock cycle to a different thread. And I'm going to come back to that first thread in many clock cycles when the data's come in from main memory. So I don't worry about prefetching the data. I don't worry about caching it so much. Instead, I just tolerate the latency because I have enough different threads that I can cycle through that I can launch a memory load, and after many cycles of working on different threads, come back to that first thread context. So context one maybe launched a memory load. And then I went through context 2, 3, 4, et cetera, running instructions from them. And maybe 10 clock cycles later, or let's say 8 clock cycles later, I just go through this in round robin. I come back to context 1, and the data that I wanted to load is available. Okay, it's been brought into my register file, and I do something on it, and then I go on to the next context, and so on. So they do have some caches. So the caches, though, are mostly, originally they were all programmer managed. So in a processor, the caches are back here are basically invisible to the programmer, right? You don't worry about it. You just write programs where you're talking about main memory, and the hardware figures out what to put in the cache. In GPUs, I'm going to talk about some convergence, but traditionally GPUs didn't do that. They said, no, the programmer is going to decide when something comes in from main memory, and they put that in a very large register file, or they put it in a shared, explicitly managed scratchpad memory. But the programmer decided what to do. The hardware was not going to figure out what to keep in a cache. So this is all about tolerating latency. Have many threads, have the programmer say where to put all the data, so you get it in the register file or the shared memory, so it's close. These two changes mean that this is really not oriented to getting an answer on one thread quickly. It's about batch processing or throughput processing. So the idea is I've got a lot of independent work to do. I don't care about getting any one piece of work done really fast. I care about getting a lot of work done in aggregate. And again, this matches graphics really well. You think of a screen, you have millions of pixels. You don't care about computing pixel number 23 really fast. You care about when all million pixels are done. So whenever you need to wait for something to come in from main memory or some long-running computation, you just switch to a different thread, which is computing a different pixel. But it turns out that programming model is useful for more than just graphics. So it's been shown to be useful for a lot of applications that have that style of parallelism. And one of the applications, so some of that is mathematical things, like high performance computing, where you're doing matrix operations. It turns out that you can arrange matrix operations in a similar way, and you can arrange machine learning. So machine learning has become obviously a very big market for GPUs too, because you have lots and lots of neurons basically, and you need to compute the outputs of all the neurons in one layer in a neural net before you can go on to the next layer. And that has some similarities to how you want to compute all the pixels on a screen. So it fits this mode well. Okay, any questions on that? Does that make sense? Okay, so that's GPUs in one slide. So, okay, so I mean, I talked about these things as completely distinct, but the truth is there are some parts where they're overlapping. And what everybody does who's smart in any field, right? So in industry, if your competition is doing something well, you should actually copy them. Okay, you shouldn't be too proud to copy. So CPUs and GPUs do copy from each other's playbook. So you'll find there's some blending where it gets a little harder to draw. You can still certainly draw a line between them, but the edges of the line get a little blurry. Okay, so how are those edges getting a little blurry? Well, CPUs are adding more cores, more floating point units, more threads. So that makes them somewhat less oriented towards just single thread performance, and gives them some aspects of they care about getting a lot of work done when there's a lot of parallelism. So cores less than GPUs, they can do about 4 to 24 cores nowadays, again, depending on whether it's a low end or high end CPU, but it's, unless you're getting very low end microcontrollers, you're probably not going to get just one core. As I said earlier, CPUs incorporate SIMD. And again, everything beyond probably low-end microcontrollers will have SIMD. And it's gradually getting wider. So if I take Intel CPUs, they went from no SIMD, they just always operated on scalars or individual numbers, to integer SIMD, which they called MMX. And that came in a long time ago. That came in more than 20 years ago. And was actually one of the things it was very good for was to try to make graphics a bit better in the days when you didn't have GPUs beside every CPU. Then they went to allowing single precision floating point, which they called SSE, and they could do 4 operations at once. So you take a group of 4, whoops, we'll go back again here, sorry. So basically what this means, let's see if I can draw on this without having it advance. So you would have the basic way the SIMD works is an instruction that specifies add. Instead of adding one number, let's take SSE, which is a 4 wide SIMD. It'll take 2 registers. Instead of those registers being 32 bits, which is enough to store a single precision floating point number, they would be, oops, sorry about that. They would be 128 bits. And you'd add them, and that would produce 128-bit output, which again is 4 numbers in it. Okay, so we've got a 4-way parallelism with one instruction controlling it. You need to get 4 numbers nicely lined up in your each of these registers, and then you can add all 4 pairs in parallel. And one way you can get more parallelism is just keep making the registers wider and keep adding more and more kind of functional units that work in lockstep. So let's see if I can get the, whoops. Okay, I don't want to do that either. So, okay, so I'm going to be careful about what I tap on this. Let's see if I can change my pen color. When we went to 8-way SIMD, what Intel did is they basically just added another 4 items on each of these registers, and they added 4 more floating point functional units. So that was the change going to AVX2. And then they've continued to widen it. So Xeon Phi was Intel's x86 processor. So it was a processor that ran the same instructions, same binaries as their regular processors, but it was intended for high performance computing. So it used a larger number of cores, but they were simpler. So it didn't do the out of order circuitry. It kind of stripped down the processor so they could fit more of them on one die. And it went for wider SIMD. So it went for 16-way SIMD. In Intel's most recent processors for data centers, so their Xeon series, they've done the same thing. They've called this now AVX 512, and it's 16-way SIMD. So the processors are gradually getting wider and wider data paths, from 1 floating point number to the latest Intel processors are up to 16 floating point numbers that can be manipulated in parallel with one instruction. Another way that SIMD effectively gets wider is if you take this same data path. So the data path that I drew here, let's see, that was 128 bits, and then it went to 256 bits at this point for AVX2, is to actually make the operand smaller. So if I take that same number of wires, same width of registers, and I operate on 16-bit operands instead of 32-bit, then I actually have well, if it was 16-way SIMD that I had for AVX 512, I'd actually have 32-way SIMD. And Intel's done that as well. So in their absolute latest processors, they can work on something called BF16. So it's a 16-bit floating point operand side. The B stands for, well, people say at least it stands for brains. This is a neural network friendly 16-bit floating point representation. With that smaller representation, you can basically get twice as much SIMD. You have to make sure that you have 32 functional units. So your functional units, you have to change, but your registers already have enough bits. Your data paths already have enough wires. So another way that you get more SIMD, go to lower precision numbers. That's particularly helpful with machine learning because machine learning is tolerant of low precision. If you're doing scientific computing and you decided, you're working with big matrices, and you're going to go to 16-bit floating point, it's just not going to work. The round off is going to destroy you. It's not going to work at all. But for machine learning, it does work. The calculations are very tolerant of round off. So, this is really driven by the needs of machine learning. All right, so SIMD's been a big one, right? So we changed cores quite a bit. We've changed SIMD quite a bit. And then CPUs also, most CPUs nowadays that are high-end have a small ability to switch threads, but much, much less than a GPU. So yeah, I see actually people talking about like my core count is outdated, is 24 too low or too high. It's true. When I was writing this, I was thinking, what should I put in here? There are CPUs that have 64 simpler cores. So I mostly went with, where is Intel with their Xeons? But I've seen a couple of people correctly pointing out that CPUs can go higher than 24 cores, usually by having somewhat simpler cores. So it's true, there's no hard limit on this. Okay, so let's talk about switching threads though. So most high-end CPUs have two-way hyperthreading these days. What that means is they replicate some of the processor state. Processors don't have that many registers on chip, so you can wind up basically replicating the register file, or you can actually tag some of the registers to say which thread they came from. And you can basically interleave instructions in one core from two different threads. And because a modern CPU core has quite a few functional units, you can get more throughput that way. If one thread doesn't have that many instructions, or maybe any instructions that are ready to execute because they're all waiting for data, maybe the other thread does. So they have that is a throughput computing concept. Have multiple threads, so if one of them can't make progress, do something on the other one. But they're using it much less than GPUs. GPUs, basically, you need to have a lot of threads running to tolerate the fact that all of your operations tend to take a while to produce their output. And CPUs are kind of using this a little, GPUs a lot. Okay, so that's why I'm saying they still have a heavy focus on single thread performance. Part of that heavy focus is they tend to target high clock rates because that is a good way to get more instructions from a single thread through and get better performance. And one of the things that I'm marking here is on assignment 2, one of the things we're going to ask you to do is actually compare the throughput on a few different compute devices for a filtering or a convolution application that we ask you to work on. One of the devices you'll compare are the UG machines. So it's important you know what's in those. So those are 4-core CPUs. They're built in a 22 nanometer process. They run at 3.6 gigahertz. And because of the processor generation, they're AVX2, so this one, which means they support 8-way SIMD with floating point numbers. So that's kind of a snapshot in time of a reasonable cost CPU from a few years ago. 22 nanometers, that's what you could get. And I see there's a question from Camilo. How does low precision SIMD deal with carry out? Yeah, you wouldn't want the overflow to hit the next register. Yeah, so you're asking, you can't basically just add these numbers together like this 256 bits register. Your functional units can't treat it as if it's one 256 bit number. So you actually do have to have for this example I'm showing here, you would have to have 8 32-bit floating point units. You can't just have one 256-bit wide adder, because you would not get the right answer. You'd be corrupting some of your outputs. So if it's integers, you can sometimes reuse some hardware by doing tricks like cutting the carry out and so on. For floating point units, you probably just build 8 separate 32-bit floating point units. So there is a significant cost to this. It's not like widening your SIMD width is free. You are building a lot more functional units. You are widening your data paths. But basically, you aren't paying for 8 times as many instructions and all the control logic to try to keep 8 times as many instructions in flight, which is much more expensive still. But you put more burden on the programmer. The programmer has to go find, 8 floating point operations that are all exactly the same type. They all have to be multiplies, they all have to be adds, or they all have to be adds or whatever. Grouping them together in these big registers, and then one instruction will, multiply them all in pairs or add them all in pairs, etc. Does that make sense? So I guess to that question, it's basically the programmer has to explicitly ask for these SIMD instructions. And the SIMD instructions have very precise semantics. They're basically packing, let's take 32-bit floating point. They're packing 8 32-bit floating point operations together. So 8 pairs of numbers will be added. And that's precise. The programmer has to be sure that's what he or she wants. If you didn't get all of the data in the right spots in the registers, then it's not going to work. That's your job to get it all there. Does that make sense? And then another question is, if the AVX instructions are not used, are these extra registers and FUs just idling? Yeah. So basically, if you don't write, compilers are not really good at using these SIMD operations, by the way. They will try to use them. It's usually called vectorization in a compiler, but they're not really good at using them. Because if you just take standard C or C++ code and you go try to find groups of 8 floating point multiplies that are all can be arranged nicely in registers and so on, compilers are not very good at that. They can do it for certain simple pieces of code, but the common way that people use these operations in C or C++ code is they actually use something called inline compiler intrinsics, which almost looks like inline assembly. So to use this does take more care. You at least got to organize your data very carefully. It has to be an application that's doing things like vector or matrix math or filtering, or something where the parallelism exists. And then usually the compiler will not find it unless you're very careful in how you arrange your data, or even better, use these compiler intrinsics to basically say, I'm going to use these special instructions and get more throughput. Does that make sense? And if you don't do that, which is the common code, common code that you just sit down and write, you didn't think about this at all, it's not going to use these SIMD instructions. They are not going to be used, right? So all these extra functional units, all these wider registers just won't be used. They will consume area. They'll be power gated, so they won't consume much power. So processors care about area. They probably care even more about power. So at least you'll save the power, but you will waste some area. And that's kind of the thing that's limiting how wide can they make the SIMD. It's gradually getting wider and wider as the area budgets increase, even though many programs will not use these SIMD instructions. Okay, so those are good questions. Any other questions in that vein? Okay, so in that case, I'm going to go on. Okay, so GPUs. So again, I'm going to do this from 10,000 feet because it's definitely, you can spend an entire course on like GPU architecture and all the details of where GPUs are going to. And I'm going to try to give a couple high-level concepts. So I picked a picture on the right-hand side here of NVIDIA's Maxwell architecture, which is their 28 nanometer GPU architecture. So, 2 or 3 generations behind. It's not the absolute latest. Why have I shown you this one? First, it's not that different in more recent GPUs. And secondly, these are the GPUs that are in the UG machines numbered from 51 to 75. So again, for the next assignment, we want you to do some comparisons. These are the GPUs you have available to you. So, and they're a little different in process technology. Best practice in comparing performance is you do it in the same process technology. So this is not quite the same as the CPU. So that's something to be aware of and to try to adjust for. Okay, so what's in this chip? It has 16 streaming multiprocessors, or SMMs, and that's NVIDIA terminology. And so what is a streaming multiprocessor? And I'd say NVIDIA doesn't really tell you this. Well, they use their own terminology, so it's a little hard to figure out. But this is my interpretation of what a streaming multiprocessor is. What's shown on the right-hand side here is a single streaming multiprocessor. So there are 16 of these in a chip. So we're not showing you the whole chip. Each of them has 4 groups. Okay, so if you look at this, these are the 4 groups. That's kind of the heart of this streaming multiprocessor. And inside each of those, if you count up these cores, these green cores, there are 32 of them. Okay, that's what NVIDIA calls a CUDA core. So if you multiply 4 times 32, you get 128 CUDA cores, and that's what they claim for this device, 128 CUDA cores per streaming multiprocessor. But they're not grouped as just one set of 128. They're kind of grouped into 4 sets of 32. Why are they grouped into 4 sets of 32? It's basically to give them a little more flexibility on what instruction each one is executing. So all 32 of these cores here are going to be executing the same instruction. And basically you've got most of your CUDA cores are floating point units. But you also have some load store units, and you have some special units for unusual operations. But the heart of the computations the GPU is good at are floating point computations. And basically every one of these CUDA cores is a floating point execution unit. So each quarter of the streaming multiprocessor is a 32-way SIMD set of floating point units and a few other units that can help them, like load store units to keep data streaming in and so on. So this is, if you put this in kind of processor terminology, this streaming multiprocessor is quite a bit like a 4 issue, meaning you can send out 4 instructions every cycle to 32 that are each 32-way SIMD. Okay, so that's probably the closest thing it is in a processor core. That makes it more flexible than a single 128-way SIMD core. It's probably kind of in between those two things. It's not as flexible as I can just execute 4 arbitrary instructions with no restrictions that are each 32-way SIMD, but it's more flexible than I have to execute 1 instruction that's 128-way SIMD. Okay, so how is this different than CPUs? Well, the SIMD is wider, right? No matter how you divide it up, this is a wider degree of SIMD than processors have. Because I talked about processors, at this generation, we're about 8-way SIMD. The absolute latest is about 16. Depending on how you count, this is more than, it's 32-way SIMD, but grouped into bundles of 128 or kind of 128-way SIMD with some extra flexibility. It has explicitly managed scratchpad memories. So it's got these up here. Let's see if I can erase some of this. These large register files. Okay, so it's got really large register files so that it can have a whole bunch of live values for different threads. Different threads can be using different registers. So it's got 16,000 registers for each one of these 4 pieces of the streaming multiprocessor. And the reason for that is, again, to allow many threads to overlap, each of them using different registers. And you can leave your value lying around for a long time before so many other threads have executed that somebody needs your register value again, which lets you tolerate latency. They also have some shared memory down here. It's kind of a local scratchpad memory. And that's also explicitly managed. So both the register file and the shared memory, the programmer is responsible for figuring out what data is in there. To go out to main memory is hundreds of cycles. So part of getting performance out of a GPU is you got to be careful about what's in these memories that are closer to you. So yeah, all of this makes it higher performance for highly parallel applications than a CPU, but also harder to program. And GPUs have gradually added in some features that are a bit more CPU-like to make them a bit easier to program. So let's take this chip. What I've circled here, and the font is a bit small because I just stole the picture. is texture cache, which is useful for graphics, or a level 1 cache, which is useful for general computation. So L1 cache means I can actually, basically I can have 24 kilobytes of hardware managed cache for each one of these streaming multiprocessors. So that helps me. So basically, if I didn't quite get everything, all my data in the right spot, the hardware will figure out some things that are coming in from global memory over and over again and help me. So that's trying to make this a bit easier to program. But that's, for a pretty beefy core like this, that's a relatively small amount of cache. So they're not spending as much silicon on caches as a CPU would, because they're just trying to help programmers cover some programmer mistakes. They're still really relying on the programmer to get the vast majority of the data in the right spot in these register files and shared memories. There's also a 2 megabyte hardware managed L2 cache, and that's per chip. So there are 16 of these streaming multiprocessors. They all share one big L2 cache. It's again kind of to cover, maybe there's some data reuse that's a bit tricky for the programmer to figure out, some things that are going to go wrong, and just cover those mistakes rather than mean that the programmer doesn't have to think about data transfer. And they target lower clock frequencies. Because they've got so many function units and power's an issue, they run at lower clock frequencies. Like this one runs at 1.2 gigahertz, and they really haven't changed much since then. Any questions on that? Okay. All right, so DSP processors is another one that you probably haven't heard as much about, but it's another important class of processors. So these are optimized for signal processing. It's one of the things that FPGAs are really good at, so I'm talking about them. They have simpler control, and they focus on loop processing, and they have lower power targets. So they focus a lot on processing per watt rather than peak throughput. GPUs have primarily focused on, what is the peak throughput you can get without melting the chip. DSP processors focus on being very, very power efficient. Get as much processing per watt as you can. They're optimized for multiply accumulate, because that's what signal processing is mostly about. And sometimes they separate their program and data memory, which most other processors don't do. So a couple of them that we actually have in labs at U of T. So I think in past years, I've had students do comparisons of efficiency versus DSPs, but I think because we can't physically get to these ones this year, you're probably not going to do those comparisons. We'll figure that out in the next week. But I'm going to describe a couple of the DSP processors that we have in labs at U of T anyway. So TI is a big name in DSP processors. They have multiple series of DSP. So one is the C6000 series, and it's focused on very power efficient signal processing. The power budgets are really low, about 100 milliwatts per chip. They have on-chip single port and dual port RAMs. And they're not very big. So you can see here's a single port RAM, and it's like 256 kilobytes, dual port RAM that's 64 kilobytes. So relatively small amounts of on-chip memory. They're explicitly managed by the programmer. So again, they're not caching things for you. The programmer uses DMA engines to bring in data, put it inside of these memory arrays, and do efficient signal processing. So it's all programmer controlled data movement. This particular chip has two integer multiply accumulate units. It has address units to load the data in, and it's a very CISC instruction set, so complex instruction sets. This would be an example of an assembly instruction. So it says repeat, load with update. So that's basically load in something using a register that's an address pointer, update that address pointer to the next element, and do a multiply accumulate on it. So this is one assembly instruction, which basically implements an entire signal processing loop. Walk through a bunch of data in memory, loading it in, and doing a multiply accumulate to compute a dot product on it. So that technique for low performance targets can actually be pretty power efficient. That's why TI uses it in this architecture. The instructions encode exactly what they need for that application domain and keep their limited number of functional units kind of completely busy with very little instruction fetch happening. Do you think this is easy for a compiler to generate code for? So type in the chat. Well, this is like one of those questions. Is a yes or a no. So you got a 50-50 shot either way. So what do you think? Think this is easy or hard to target? Yeah, so Marius says no. Everybody says no. Okay, so we've got a few people here maybe taking compiler courses. Yeah, you don't want to write a compiler for this. So humans can get much more performance out of this processor with careful fine tuning than a compiler can. It's a pretty difficult compiler target. But because it's targeted at signal processing, TI has a bunch of highly optimized assembly libraries. So you can kind of stitch together signal processing applications without writing a lot of high-level code, because compilers don't do as well with this. Okay, so TI, that's kind of TI's series of very low power, but also quite low performance DSPs. They have higher performance series as well. So this is the TI C6000 series. Its architecture is different. So instead of using CISC, where it's really best targeted by somebody writing assembly language, this one's intended to be targeted by a compiler, because as you get into more complicated applications, you probably don't want to write that much assembly, and you might not be able to get all prepackaged functions from TI. What this particular chip has is it's VLIW. So it's got a bunch of execution units, but they're all different. And the instruction word basically packs together control of them all. So it's got 4 address or memory units. That's what it's showing down here. So memory units. Actually, I think I did that wrong. So 4 address memory units are these load store units here. It's got 2 Macs. So Mac here, Mac here. And those can be split up. So they can basically use the same SIMD trick. So it can either do one floating point, or it can be divided up into 2 fixed points. And we talked early in the course about how register files and central storage, like central storage tends to be a bottleneck. It gets expensive. You need a lot of ports to read and write to a central storage file if you have a lot of functional units. So what TI did, because they have quite a few functional units here and they want to be power efficient, is they partitioned the register file. So you see they have a register file A and they have a register file B. And certain functional units can talk to register file A. Other function units can only talk to register file B. And there are a couple that can move data between them. So you're not completely stranded. But they did that in order to, again, be more efficient and target a low power. They don't want to have that many ports on their register file. So to get to a higher performance target, they largely partitioned it. They have later and higher performance DSPs where these multiply accumulate units go further with SIMD, which is often called vector. So SIMD and vector processing are used somewhat interchangeably in the processing community. So in their later versions, each of these multiply accumulate units could do 4 single precision operations or 8 16-bit. So they mixed VLIW with some SIMD. Okay, so in this series, you can also explicitly manage memory, or you can have hardware manage it as a cache. So yeah, by explicitly managing it, you can get more deterministic performance, like be guaranteed you're going to be done in this many cycles, and sometimes get better performance than letting the hardware manage it as a cache. But for ease of use, they also let you turn on hardware management of the RAM if you wish. So basically, as chips get more complicated, it's most efficient to let the programmer manage everything. But as the chips get more complicated and the programs get more complicated, sometimes it just becomes infeasible. So you see the more complicated chips start adding in more hardware management. Okay, they have a lot of variants of this. They have some that only have fixed point, multiply, accumulate, some that only have floating point, some that have both. To get more performance, they can take what we just talked about, which is basically a DSP processing core, and they can put multiple cores on one chip. So instead of 1, they could have 2, 4, or 8. They also combine these with hardwired accelerators. So TI's DSPs are not really trying to be general purpose devices that are going to go out, and they're not going to go into a data center and compete against Xeons. They're going to go into embedded devices. They're going into, cars, cell phone base stations, some of the same things that FPGAs go into. So in those applications, they often know what some of the other processing is. So they'll put hardwired accelerators in beside the core. So some variants of these DSPs that have no accelerators, other ones will have fast Fourier transforms, Viterbi decoders, etc. So they know some of their target market, and they'll put hardware blocks beside these. And in some of them, they'll actually include essentially a housekeeping processor, like a lower performance ARM processor that's kind of easier to program and good at control tasks, besides the C6000 Series DSP, which will handle the heavy lifting of signal processing. And they target a wide range of power. So I told you that that earlier one, the C5000, targets about 100 milliwatts. These ones are more, but they're in the 1 watt to 20 watt range. So still not super high. And to get up to 20 watts, you have to buy one of the really fancy multi-core ones. Okay, so a summary of kind of the processor landscape. So DSPs, CPUs, GPUs, those are all versions of processors. We've got different power budgets. So they range from about 100 watts for a high-end CPU and about 300 watts for a high-end GPU, all the way down to sub 1 watt for a low-end DSP and maybe 20 watts for a high-end DSP and a pretty high-end FPGA. So FPGAs traditionally had power budgets in the range of 1 watt for a small FPGA, maybe even less for very small FPGAs. And the biggest, fastest FPGAs had power budgets of around 20 watts. And that was actually true for many process generations. The FPGA capacity kept going up, but by scaling the voltage and the capacitance, you could keep the power around the same. That kind of broke down at about 14 nanometer. So in 14 nanometer and later high-end FPGAs, this would be like Xilinx UltraScale and Versal and Intel Stratix 10 and Agilex. The power budgets for the biggest devices can be 100 watts, which is a lot bigger than FPGAs used to be and is getting up into the range of the high-end CPUs. So mostly FPGAs have been in this range where DSPs are. But yeah, recently some of the high-end devices, at least that are really big, are more pushing into the higher power numbers, which they really would rather not do, but it's enabling more performance. Okay, so there's some convergence between these things. They're sacrificing some performance for ease of programming. So you see GPUs and DSPs bringing some caches in, and DSPs, you have fixed point DSPs, but now you also have a lot of floating point DSPs that are easier to program because you don't have to worry about round off as much, but they're less efficient. Floating point multiply accumulate is more complex than just using integers. So if you do everything using fixed point or integer math, it is actually more efficient in terms of hardware, but it puts more burden on the programmer. So the trend has been to let people use floating point more. Whoops. Everybody's leveraging SIMD. So DSPs are using it a little bit, CPUs more, and GPUs a lot. There's some divergence. So CPUs still spend much more area on single thread performance. GPUs get their throughput by tolerating latency and having many threads rather than trying to make any one thread run fast. And DSPs tend to rely on explicit scheduling and programmers controlling the data movement to stay busy. So they can do well with single threaded code, but they basically need the programmer to carefully move all the data into the on-chip RAMs in advance and so on. Okay, so we compare this to FPGAs. They rely even more on explicit scheduling and data movement. So they're harder to program if you're trying to use one of those simpler or more hardware-friendly programming models than even a GPU. So you can create a custom and highly distributed memory system. You can create a custom processing pipeline. So they really rely on very explicit data movement. They're best at small data types and good at integers. So why are they better at small data types? Let's throw out a question there to make sure everybody's well, maybe not everybody, but at least someone is awake. We'll see if anybody comes in. So saying FPGAs are, yeah, best at small data types, pretty good at integers. Why? I guess you gave me part of the answer. They're weaker at floating point. So, but why would they be weaker at floating point, better at small data types?
Because smaller data types require smaller computational units, which can be easy to route on the FPGA.
Yeah. So an FPGA is able to adapt to the size of operands that you need. So yeah, if you just need 4-bit multiplication, you can build 4-bit multiplication. And if you never need to multiply, you just need adds, then you can build those. So that means you can fit a lot more functional units on the chip if you're using small data types than if you're using big data types, just because your functional units are so much smaller. That's much less true in CPUs and GPUs. So in CPUs, most things are going to be done well, whether you use them or not, there are a bunch of floating point 32 units in those SIMDs. So you can code everything using some other data type if you want, but all those function units exist. They're chewing up area on the chip. Same thing for a GPU. There's a little bit of a caveat on that. I showed you that CPUs and also GPUs can do things like floating point 16. So if you can use floating point 16 format, then they have built more small functional units for those formats and you'll get more throughput. But basically you're paying for what other functional units have been built in those devices. Whereas in an FPGA, you only pay for what you use. That is the biggest win when you're doing small data types where basically other devices have overbuilt. They usually have built support for much bigger data types and you're just not using it. Floating point hardware is a lot bigger than fixed point hardware because you have to keep track of where is the decimal point. You have to shift your mantisses before you add them. That's a bunch of extra hardware, right? So, and in an FPGA, you have to build that. Traditionally, you had to build a bunch of that out of the soft logic. So if you had to, I don't think I want to draw this on a slide. If somebody's interested in the break, you can ask me to draw why is a floating point adder or multiplier bigger. But basically, there's a lot of shifting of the numbers to get the decimal points aligned. And that's pretty expensive in soft logic. And historically, that had to be done in soft logic in an FPGA, whereas in a GPU or a CPU, they built it in hard logic, so it's more efficient. That's changed in recent FPGAs. So Altera's ARIA 10 device added hardened floating point units to the DSP blocks. So all FPGAs before that, their DSP blocks could do basically integer multiplication or integer multiplication and accumulate. And ARIA 10 basically added a relatively small amount of hardware by using some clever tricks so that they could actually do floating point in the DSP blocks. So suddenly floating point became not more efficient than fixed point. Fixed point still, if you can do it in fixed point, it's still more efficient on an FPGA. It'll take somewhat less hardware. And if it's a small precision fixed point, it'll take a lot less hardware. But it suddenly made the floating point hardware on an FPGA essentially as good as what would be in a CPU or a GPU. It's not really better. It's just basically it's around as efficient because it's built out of mostly hard logic. When this happened, it wasn't clear that was a good idea because it does add some area to the DSP block. And if you're a clever enough engineer in the signal processing domain, you can actually figure out for the vast majority of algorithms how to map it to fixed point and get an even more efficient implementation. So I was at Altera when this decision was being made, and it was a somewhat controversial one because you could say, well, signal processing engineers are just going to move everything to fixed point because that's more efficient in the long run anyway. So we're just going to add some hardware to the chip and it's going to be a waste. The reason it went in is it was made relatively cheap. It only added 10% to the area of the DSP block, which added well under 1% to the whole chip cost. And because high performance computing, people who are trying to write high performance computing code, so they're trying to solve matrix equations and so on, they are much less tolerant of fixed point. They don't want to do fixed point. So if you're modeling physics, usually like I'm starting with floating point and maybe double precision floating point. it has now become clear that this decision looks like it was the right one, because the follow-on devices from Intel have kept the hardened floating point units, and now Xilinx has added them in too. So usually in the FPGA industry, once both of the big companies in it, which are Intel and Xilinx, have put something in their chips, then it's going to be really hard to get out. When one of them puts it in, maybe they made a mistake. Once the other company decides to do it as well, it usually has become a standard. Okay, and the big difference, maybe the biggest difference between FPGAs and these other processors is it doesn't need an instruction stream. So as we talked about in programming models, you can make an instruction stream, but usually for your heavy lifting, you won't have an instruction stream. It's very common to do that as a streaming style of hardware for the most critical computations, and those don't need an instruction stream. All of these other types of devices need an instruction stream, and then they basically do tricks, right? Complex, important tricks to try to use SIMD or multi-threading or other techniques I guess SIMD would be a big one, to reduce the cost of that instruction stream. Okay, and that's all I have to say about processors and FPGAs from 10,000 feet. Any question on this? Oh, and I see Camilo had a good answer on why are FPGAs better at small data types, because they can do arbitrary precision. So yeah, you build what you need. So any questions on any of this? Okay, doesn't look like, so let's take a 10-minute break then. And then we'll go on to the first reading. And talk about what it has to say about essentially peak performance on a bunch of different devices. So let's take 8 minutes. We'll meet again at 5:20.